Hello friends, this is a consolidation video about nuclear physics. It is actually summarizing nuclear physics with just one short test. One of my students told me to record this about these questions, so I had to record about them. It's just from one of the tests which I gave my students. You can call it nuclear physics part 3, there's no problem, but it's a very short video. It is just about a few questions which my student thought they are quite still challenging to them. So please, without wasting any time, let me take you to that short document. It is a short document. You may not be having it, but you may just use it for reference in case you also find similar challenges. Okay, let's go to the document. So it was an end of unit test. The first question is easy. Define radioactive decay. We know that radioactive decay constant lambda, this is the radioactive decay constant lambda. We know that this is the probability of decay of a nucleus, probability of decay of a nucleus per unit time. That is a decay constant. A sample of radioactive iodine 13153 has a mass of this and has an activity of this. Determine the decay constant lambda. So we know that from activity is equal to decay constant times n. Of course, we need n. From n over number, Avogadro's number, equaling to mass over molar mass, we can find n. So n will be the mass, which is 5.67 times 10 power negative 10, divided by the molar mass of iodine, which is 131. Since this is in kilograms, we shall also change this from grams to kilograms, so that is times 10 power negative 3. This is the molar mass in grams. So this will be times Avogadro's number, which is 6.02 times 10 power 23. So that is the number of nuclei. So we just go to the decay constant lambda being equal to activity, which is 2.92 times 10 power 9. Of course, I'm going to divide by n. I'm making lambda the subject from that equation. So when I divide by n, I get the reciprocal. So this is 131 times 10 power negative 3 divided by 5.87 times 10 power negative 10, then times 6.02 times 10 power 23. So I press my calculator to find lambda. So from my calculator, lambda is divided by 6. So my calculator is giving me lambda as 1.08 times 10 power 6 per second. Suggest two reasons why a detector placed near to the sample would record a count rate much less. Why the detector would record a count rate which is much less? There are several reasons. Number one, the random nature of radioactivity. The random nature of radioactivity. Or radioactivity is being random. The sample emits radiations in all directions. So yet the detector could be unidirectional. In other words, we would say the sample emits radiations in all directions. Because emission is random. That's number one. Number two, it could be as a result of self-absorption. Maybe the emitted particles are absorbed within the sample before they reach the detector. So self-absorption within the source. Self-absorption within the source may also reduce the count rate, may make the count rate much less than expected. There could be a dead time or inefficiency of the detector. 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 There could be a time when the detector is not working or it is inefficient. That could also make the count rate to be less. By the way, some radiations could be absorbed in air. For example, gamma rays do not have a small range in air. So some radiation is absorbed. So if radiation, the detector is some short distance from the source, some radiations may be absorbed by air, so they may not actually contribute to the count rate. So that would make the radiations to have, the count rate to be much less small. So those are some of the reasons I could think about. Number two, the last question. Radioactive decay is both random and spontaneous. State what is meant by random. We said random means we cannot predict which nucleus will decay next in a given sample. So random cannot predict which nucleus in a sample will decay next. Then spontaneous, we have said it's spontaneous. Decay is not affected by external factors. Decay is not affected by external factors or environmental factors such as temperature, pressure, catalysts, etc. I think this was the hardest question to this student. A sample of radioactive material contains atoms of an unstable nuclide X. The activity of the sample due to the atoms of X is A. The variation with the time t of ln of A is shown in the figure below. Remember, we know all along that activity is equal to A naught e power negative lambda times t. When we divide both sides or we introduce a natural logarithm, you notice that ln of A is equal to ln of, I'm introducing natural log both sides, is equal to ln of A naught plus ln of e power negative lambda t. But remember, ln of e power negative lambda t is just the power. So it means ln of A is equal to ln of A naught minus lambda times t. Compare with the y equals to mx plus c. On the y-axis, we have ln of A. On the x-axis, we have t. So you will notice that the gradient of this graph is going to be negative lambda. Let's see the question. The question says use the figure to determine the half-life in minutes of nuclide X. So we have already seen that ln of A is equal to ln of A naught minus lambda times t, which means if we plot a graph of ln of A against t, the gradient is negative lambda. So the gradient is equal to negative lambda. So I try to find the gradient. So the gradient will be negative lambda. Let's try to find the gradient. So the y values we have, this is I think 36 point. The scale here is 0.4 divided by 10, that is 0.04. So 1, 2, 3, 4, 5. So times 5, that is 0.04 times 5, that is 0.2. So that is 36.4. So we have 36.4 minus, it goes to 0, so minus 0. I mean not 0, it goes to 35 on the vertical. So minus 35.0. Divide by the x-axis, it starts from 0, then minus, I think it stops at 20. It stops at 20, so it is 0 minus 20 on the x-axis. So the gradient is negative, but gradient is negative lambda, so it means lambda is going to be equal to, the gradient itself is, this is negative, but then there's a negative here, so lambda is equal to, so lambda is 0.070 minutes, per minute. Decay constant is 0.070 per minute because I didn't change the values of time on the x-axis, so it is per minute. On the vertical axis is ln, which is a constant, a ratio. Then half-life, we know that half-life is ln of 2 divided by decay constant, so it will be ln of 2 divided by 0.070. This is giving me 9.902 minutes. For the first time, I'll be forced to write this as approximately 10. But if I don't round off this, it is, let me check again, 3.64 minus 35 divided by 20. 36.4 minus 35 divided by 20. Then I have ln of 2 divided by the answer. So that is 9.902 minutes, or approximate if you want. This one is inevitably approximately 10. Okay. Then at a time t equals to 0, this is the last question, at time t equals to 0, the mass of the atoms of X in the sample is 5.66 times 10 power negative 7 kilograms. Determine the nucleon number of X. Determine the nucleon number of X. So we already know that activity is equal to lambda times n. Activity is lambda times n, decay constant times n. So the activity, we have already seen that the decay constant is 0.070. We need the number of nuclei because remember, to find the nucleon number, it will be the mass in grams. The mass in grams over the nucleon number in grams is going to be number of nuclei over Avogadro's number. So since we want the nucleon number, we want MR. Small m has been given. So we need n. We need n. So from the which one is easier for students? So I am saying where there is nucleon number, I will put there A, because where there is a nucleon number of X, where there is molar mass, the molar mass, I'll put there A because I'll maintain the answer in grams, but it means I'll also have to change this one from kilograms to grams. The molar mass is actually in grams, is actually the nucleon number. But what is N? What is N? So we have already seen that here the initial activity from the graph, we see that when t is 0 at t equals to 0, ln of a naught is 36.4. So I've just used the original expression that ln of a naught is 3.6. I mean 36.4 is 36.4. That is ln. So I can get a naught. You can get a naught here. So it means also know that, which formula should I use easily here? So ln of a naught is 3.6 times 4. So we can get the ant logarithm to find a naught. So a naught is going to be equal to e power, I think it is e power 36.4. That is, yeah, I think that is correct mathematics. And a naught is going to be equal to the decay constant, remember, times the number of nuclei, or times the nucleon number. So the decay constant, we have the decay constant as the decay constant was 0.07. Lambda is 0.070. This was, remember, per minute. That is 0.070 over 1 minute. So I will change it to per second, so it will be 0.070 over 60. So that is now per second, because 1 minute is that. Okay, I was just looking for a simpler way of doing this, but this is fine. So the activity, which is going to be e power 36.4, should be equal to the decay constant, which is 0.070 over 60 times n. From this expression here, you notice that n is going to be mass over the molar mass times Avogadro's number. So this will be times n, which n is mass, that is 5.66 times 10 power negative 7, again times, I want to change it to grams. I want to change this mass to grams. So how do we change this to grams? It's 5.66 times 10 power negative 7 kilograms to grams. I multiply it by 1,000, so this will be times 10 power 3. Divide by the molar mass. Divide by the molar mass, which is what we want to find. I will call it A in grams. Then times Avogadro's number, which is 6.02 times 10 power 23. Okay, so I'm just going to make A the subject by just dividing. So I'll have, what is E power? What is E power 36.4? So I'm going to get this one times 60. So A is going to be equal to 0.070 times 5.66 times 10 power. Power 3 multiplied by power negative 7. This becomes power negative, I think, 4. Then times 6.02 times 10 power 23. Then I divide this by the answer I've got here after making, I'm trying to make A the subject. So this is 3.859 times 10 power 17. So I'm going to get the bracket 0.707 times 5.66 exponent negative 4, then times 6.02 exponent negative 23. So this is giving me approximately 62. 62. Let me check it again. 6.02 exponent 23 times 5.66 exponent negative 4 times 0.0 0.07 divided by 3.859 exponent 17. Yeah, it is 62. So this is 61.80. So we round off the nearest whole number, approximately 63 in grams. This is in grams, so that is approximately 62. So the process is very easy. You needed to use the inactivity. All we needed was N, that is mass over molar mass, but the molar mass is what we want to find. However, we know that the initial activity is given by 36.4 from the graph. So we could find the anti-logarithm because ln is log to base e. That's why you see a naught is e power 36.4. The decay constant was in per minute. I tried to change it per second by dividing by 60. So I now just equated the two by replacing where there is n with m over molar mass times a times Avogadro's number. So that gives me 62. I think that is the end of this short test. And I hope I've made this clearer to you. Thank you and be blessed. We meet in oscillations and simple harmonic motion.